like to tell you about that. And there are a number of aspects of this. One aspect of this is that Leibniz invented base 2 arithmetic. He heard about the I Ching from a Jesuit priest who was in Beijing trying to see if the Catholic Church could convert or communicate in some way with the Chinese. And when he heard about the I Ching, he immediately said, oh, the Chinese must do arithmetic base 2, you know, addition, multiplication, and binary. It's very neat. And a Chinese scholar from the Academy of Social Sciences in Beijing assured me, he's a scholar, a great expert on Leibniz, he assured me that in fact the Chinese did not have binary arithmetic. But anyway, to Leibniz it was sort of obvious, the idea from the I Ching. Another thing that Leibniz did was he worked on artificial intelligence. Today we are either celebrating or how do you say, commiserating that a program is giving, doing Go very, very well. Project of the time was a little different than playing Go or playing chess. The AI project of the 1600s was calculating, and Pascal had done the first calculator that could add, the Pascaline, I think it was called. And Leibniz came up with a design for a calculating machine that could multiply, and there were some mechanical problems getting it to work. He visited London and showed it to the Royal Society, and they elected him a foreign member, although as you might imagine he had a fight with Hooke. He was always fighting with everybody, including Newton. Right? So that was part of the course. So this was a great artificial intelligence project at the time, because I think in the 1600s, I think most people didn't read or write. Not very well. Priests were probably the only people who wrote or write well. And I think to do multiply then was probably a sign of a person who was brilliant. So I know that there was one pope who was regarded as practically magical because he could multiply and add and So another idea of Leibniz is to talk about binary. There's a particularly fun thing that Leibniz did, which is he got very enthusiastic with this notion of binary. He immediately saw lots of implications and possibilities of the idea of 0 and 1. So he proposed to his duke to mint, or what do you call it, a silver medal celebrating binary arithmetic. And there are two designs, I think, in Leibniz's handwriting in his papers. One is in German and the other is in Latin. But the content is roughly the same. It's something like this. There's also a table showing you the numbers from 1 to 16 or 17 in decimal and binary. years ago, it took a lot of vision to see that. And he also realized that binary arithmetic was very good for physical implementation. Very simple. I think there's some letter where he has some note to himself where he has an example of. Part of the problem with Leibniz is his ideas are scattered. There's no definitive version. They're constantly in evolution. They're in these letters, they're in these notes to himself, and most of which have not been published. People are still going through this pile of manuscripts. The handwriting is difficult to make out. The ideas are very clear, but you have to know Latin or French from birth, basically, to be able to write in Latin or French to be able to decipher them. And guess what? The ink is fading, so they should probably scan all of the surviving papers as fast as possible. Says that, we should all go there and try to find if Leibniz somewhere had the idea of a universal Turing machine. He thought that Leibniz was worthy of that idea. It doesn't, so far as we know, it doesn't actually appear. But Leibniz did have a clear idea of the importance of being able to do something mechanically. This is his reason that logicians considered him sort of a patron saint of logic. The idea that reasoning with proper symbolic system could be done sort of automatically, mechanically, like you do arithmetic. You should be able to reason with the same certainty that you say 2 plus 3 equals 5. So this is the basic idea of mathematical logic, getting the right notation to be able to do this sort of automatically. And one example of this idea of Leibniz is his version of the calculus, which I think is much deeper than Newton's version of the calculus. Now Newton is undoubtedly a much greater physicist and theoretical and experimental physicist than Leibniz, I admit it. I think Leibniz is a greater mathematician. Also, of course, Newton was not much of a philosopher. Leibniz was. But why am I saying all of this? Oh, the point of what Leibniz's version of the calculus, Leibniz wanted a formalism that would sort of brainlessly take you from the statement of a problem to the answer by just applying certain formal rules.
And then this other one, it goes from 1 over to minus 2 over. So the total length of this one is 3. So I'll copy over the picture here. This is 3, and this is 4, and this is 5. Well, this is what it turns out. Let me explain where this comes from. What you do to get this is you take this squared. So I'll write this down. 5. The rule is that 5 squared is 3 squared plus 4 squared. So what you would do to compute this is you take this thing squared and you add it to this thing squared, and then that's the distance squared. So plus AB plus BA. and AB and BA are equal to each other. So that's one way to compute the area of the thing. But the other thing you could do is you could compute the area of these 5 pieces individually. So the area, let's figure out the area of this thing. Well, this is I'll just draw it over here. Well, oops. If I stick 2 of these together, I get a B by A rectangle. So if I stick these 2 together, I get a B by A rectangle. And if I stick these 2 together, I get a B by A rectangle. So just coloring it in, if I just compute the area of these 2, I get AB. And then if I compute the area of these 2 together, I get another AB. And finally, I have to compute the area of the inside. The inside's a square, and its area is c squared. So what you get out of this is the area of the whole thing is these 2 plus these 2 plus the one in the middle. So you get c squared plus AB plus BA. But then if you look at this formula, this thing over here, it's equal to this thing over here because they're both computing the same thing. So now what you can do is you can just cancel off the things that are the same. The AB cancels the AB, and the BA is the same as the BA. So what you're left with is the formula that A squared plus B squared equals C squared.
this process of emanation is met by a process of return. So all things seek to return to the one. Okay, and this process of emanation and return are in equilibrium. So the return goes through the hypostasis. So the soul returns to nous, and nous returns to one. And the movement of return is a movement of desire. Okay, so all things desire to find to get to a more simple and more real stage. Okay, so as you go further up in this chain of being, things get more simple and things get more real. Okay, so there's a desire for that simplicity and for that greater experience of reality. Okay, this desire is nourished by and expressed in contemplation. Okay, so the way this return happens is through genuine contemplation, and that's what leads to the return. All right. So Plotinus' philosophy is an exercise in introspective self-understanding of the self. So introspective. So if you think of the word spectator or spectacle, that means looking, and intro means within. So Plotinus' philosophy is about looking within and understanding the self. So if you recall, we talked about how in our experience, that knowledge is discursive, right? Which is the idea that to achieve knowledge in the experiential world, it's a process of steps. But we said there is this knowledge of the self which is intuitive, right? You just know yourself as yourself, primarily with no medium in between, so to speak. Okay, and so this is the process of beginning to move up in this chain of being is really a process of going within yourself, and within yourself you begin to find this intuitive knowledge through that. And this contemplation of yourself, you move up the chain of being. So not just us, but really anything. What is higher? So the higher, okay, is not more remote, right? So this is sort of a counterintuitive thing. So let's say this was a mountain and this is you, right? Now what is up here is farther away than what is here, right? I mean, that distance is greater than this. And so spatially, that's the way it works. But with Plotinus, is the one, or what is higher, is actually not the more remote. Okay? The higher you go, right, it's the more inward you go.
that job was given to Watt, and he did it quite well because they actually paid him, and they asked him to set up a workshop associated with the observatory and the university. He became good friends with two professors there, the scientist Joseph Black and the economist Adam Smith. Watt is, of course, most famous for his invention of the steam engine. The story is often told that he was inspired by watching a boiling tea kettle lift the lid of it by the steam. And this is an apocryphal story, rather like Newton and the falling apple. In reality, he did not invent the steam engine, but he made a huge improvement in what existed at the time, called the Newcomen engine, which had been around already for 50 years and was used in pumping water from coal mines, but was barely efficient at all. Now, in order to show things on this, and you're getting steam all the time in this engine. You're using most of the heat from the fire to boil the water. Very inefficient, didn't work very well. What Watt has managed to do in his engine, which if decompression is needed, whatever the hell that is, what he managed to do was boil the water in a separate chamber and have only steam in the expansion chamber, and therefore it was much more efficient. Oh well, sorry. I'll see if I can't get that fixed somehow.
Thank